Hello everyone, welcome back to lecture 30. This is part 2. So, we will continue our discussion. So, here you can see these two images and both are for the same area, right. So, this is the optical remote sensing image. So, here you can see we can identify that there is some deformation, but when we look at this LiDAR imagery, so this is very evident that these areas are under the deformation. So, this is a particular landslide, right, whereas here it is very hard to identify the boundary, but here you can easily demarcate their boundary, right. So, once you do that, this flow you can also identify, which was not possible in the reflective domain images. But when we talk about this LiDAR information, this can be done using a UAV, and here you can see this is a vegetated area, and because of the vegetated area this is covered, right. This information is covered in the normal satellite images. So, rapid mapping of landslide in the Western Ghats of India triggered by 2018 extreme monsoon rainfall using a deep learning approach. So, this is done by Meena et al. 2021, and here you can see this is the study area and this is the landslide for which we were talking about, right. So, this is from the Karnataka, India. The convolutional neural network CNN is used to detect the landslide, and here they have used the 3M Planet Scope DOV optical image and 12.5 meter ALOS pulsar, right. So, these were used in this particular study, and here they have manually delineated the landslide, and the false color composite of the planet scope image was used, and then they have used normalized difference vegetation index NDVI that I have already discussed with you. So, here you can see that this map is showing the sample area, right. So, this is the sample area and manually delineated inventory that is in the red color, right. This is the RGB of that image, this is NDVI and this is the slope map, and here the minimum is 0, high is 76. So, this slope map is further used. Now, based on the input and the CNN method, they have detected the landslide, and this is the automated one, this is the manual one. So, you can see manually it is going above this. So, that means this is underestimating the landslide area, right. So, then they have also identified true positive, false positive and false negative, and this kind of images will provide you more accurate result, and this will be able to justify that whatever result you have produced is of use. In this particular one, enlarged map of the results of the CNN model showing the detection of true and false positive and false negative in the testing area. So, this A is the forest area, B is the near road network and hilly terrain, and C is your near built up area, and how these true positive, false positive and false negative are coming, right. Then we will talk about another study. This is active landslide detection using integrated remote sensing technology for a wide region and multiple stages, a case study in southwestern China. So, here you can see the elevation value, it is from 89 to 7416, and this shows the boundary of the study area. So, this is the boundary of the study area, and the blue color is the key area, right. This is the key area, and the green color is representing the river, and the major fault is represented by black color, this black line, right. So, this XSF, ANF, YBF, these are the major faults present in this particular area. And this history of earthquake, so earthquake of different magnitude greater than 7 with this size it has been represented. This size is for 6 to 7, then 4.5 to 6, and then less than 4.5. So, this map provides you the information about the seismic activity in the study area. So, situated in rare topographic change gradient belt because of this major faults, this area is also seismically highly active area, utilizes different remote sensing techniques in active landslide detection in regional and local scale, right. So, this is the workflow that they have followed. So, first was the data preparation, then they had the landslide investigation at a regional scale, then they have done the landslide detailed inspection at the local scale, and then ground survey, because you need to validate your remotely sensed images information that you are deriving for the landslide, right. So, you can go through this, you will be able to understand how they are following this methodology. Then regional scale average annual deformation phase map along the LOS radians. The figure provides a closer examination of 7 deformation hotspot areas, highlighting numerous deformation anomalies within each area. So, you can see I have marked it with different colors. So, you see this circle will appear. So, this is A, right, then you have B, then you have C, then you have D. So, these are the enlarged one, right, and then you have E, right. So, these are listed here A, B, C, D, E. The local scale LIDAR based validation for active landslide mapping. So, here you can see the A is this map is the LIDAR data and mapped active landslides along the highway from Lee County to Mau County, right. And B to D here, this B to D, it is the detailed result of the landslides, right. From left to right, optical remote sensing images, LIDAR derived DEMs, stacking INSAR annual deformation phase results, and the SBAS INSAR annual deformation rate result. So, these 4 are here, right. This is for the Tongva landslide. So, this PT1, PT2 and PT3 time series deformation rate with precipitation. So, you can see the precipitation is here, this is the displacement and this is the time or date, right. Here you can see this is the PT1, this is PT2 and this is PT3. So, how they are changing when you are having different amount of precipitation, the displacement is changing, right. So, this is with respect to time. Now, we will talk about the landslide susceptibility mapping. Process of identifying and spatially delineating areas prone to landslide based on terrain condition, environmental factors and historical landslide occurrences. So, here method that is used here. So, here the first one is the statistical method. You can go for the logistic regression, discriminant analysis, etc. When we talk about the index based method, weight of evidence, frequency ratio, these methods can be used. Now, as I said, remotely sensed images have the option to be used in your machine learning algorithm. So, you can use fuzzy logic, decision tree, support vector machine, neural network, etc. Right. Then comes the multi-criteria decision analysis, the AHP. So, here you need to have the field information, then this AHP will give you very good result. This is the flow of different methods adopted in landslide susceptibility and hazard zonation. So, here you can see the landslide susceptibility and hazard zonation approach. So, you start from here the qualitative approach and then quantitative, and there is semi-quantitative approach. So, then we can have the qualitative, quantitative and semi-quantitative. So, all these can be done with remote sensing images, because you will be surprised to know that many of the parameter that is being used in landslide studies are getting generated with the help of remote sensing, right. So, that is why all these analysis you can do it in the spatial domain, right. When you restrict yourself with the ground information and the conventional method, then those will be the point scale information. But when you are incorporating the remote sensing, it will for the larger area and we can call it spatial domain analysis. When we talk about the machine learning method in LSM, the ML algorithms can learn the relationship between landslide occurrences and conditioning factors without requiring a predefined structural model in the data set. So, what happened? Let us consider this is the study area and we know all these points are the historical landslide event in this particular region, right. Now, you want to analyze whether this X has the potential to fail or not. So, what we will do? We will generate all the parameters with the help of in situ investigation or maybe from remote sensing, that will be collected and we will generate a database. Then we will be using machine learning, and in machine learning the system will learn itself that if this particular location has failed in the past, what are the different parameters, right. So, based on that it will generate a set of relationship for all these historical points, and on that basis it will evaluate this particular location whether this has potential to fail or not. So, this machine learning algorithm can learn the relationship between landslide occurrences and conditioning factors without requiring a predefined structural model in the data, because you are defining the relationship now. And here we have some assumption. So, the first one is the future landslides are more likely to occur in areas where past slope instabilities were triggered by similar conditions. Factor directly or indirectly associated with slope failure can be utilized to develop predictive model for landslide spatial occurrences. This is what I discussed here. So, here you will have the factor analysis, then you will have model building, and then you will have the testing and validation step. What are the different advantages of machine learning? So, ability to capture non-linear relationship, because when you go for the simpler models, they will not be able to correlate n number of parameters and their relationship with the slope failure. But when we go with the machine learning, here you will have the opportunity to utilize all the historical data set as well as different parameters, and then new set of relationship will be generated. Higher accuracy and generalization. ML provide objective result with higher accuracy by learning from large data set. So, here the historical data set, the number of points should be large, then only your machine learning will help you. Better handling of large and high dimensional data. They can efficiently handle and progress higher dimension data and identify important features, because when you are talking about the parameter that is triggering the landslide, here the list is not limited to 5 or 6 parameter. It can be 10, 15, 20 depending upon your area, and that can be used in machine learning, and machine learning will be handle your high dimensional data sets. Adaptivity and automation. ML model can be updated and retrained for new data, making them adaptable. If you have generated a ML model for a landslide studies for X area, similar model can be used for the Y area depending upon the retraining. You retrain your algorithm and then your model will be able to predict. Integration with remote sensing and GIS. They can be integrated with wide variety of remote sensing data and GIS, improving susceptibility mapping, right. So, when you are having the high dimensional data and in the spatial domain, you will have better prediction. This particular slide gives you the information about the landslide causative factor used generally in LSM studies, right. So, here you can see the slope, aspect, elevation, land use, land cover, distance from lineament, lineament density, distance from fault, distance from road, NDVI, relative relief, geomorphological map, drainage density, distance from drainage, TWI, SPI, rainfall, right, and earthquake information, the historical points. All these can be generated from remote sensing, and your analysis can be done in the spatial domain. Typical illustration of some of the commonly used machine learning methods. So, here this will provide you, I hope you have seen this kind of diagram many times. This is the typical architecture of a decision tree. This is the typical architecture of a ANN, right? And this is for the support vector machine. So, what happens when you are having two groups of information and you want to segregate them, right? So, in that case the support vector machine will help. So, it will try to generate this plane that will separate this data set from this data set. That is possible with the support vector machine. Transforming non-linearly separable data in input space into a higher dimensional feature space for linear separation. So, this is very good for separating two information with respect to the landslide studies into two different groups, and that will be able to classify your data set. And in machine learning, different matrices are being used. So, various performance matrices derive from the confusion matrix, including overall accuracy, specificity, sensitivity, F score, and many other methods are used, right. Area under the ROC curve, which is known as AUC. Then you have objective function OF, then you have kappa coefficient, then you have reliability diagram. So, these all are used to test your information or to validate your results, right, that is being generated from the ML methods. Now, let us talk about the landslide hazard assessment using analytical hierarchy process AHP, a case study from National Highway 5 in India. Here it is from Kalka to Simla. This highway faces frequent landslide event in the monsoon season. Landslide hazard assessment is performed using the analytical hierarchy process. So, this is from this particular publication. So, you can see the methodology. They have used the Aster DEM, Google Earth Maps, field information, and soil map. And the Aster DEM can provide you the slope, aspect, curvature, relative relief, and TWI. Whereas this Google Earth and field data together, they are used for the landslide inventory. Then we have validation of landslide hazard map, and here the soil map will provide you the geology, lithology, fault density, drainage density, distance from road. All these are together used, and then it goes to the AHP, right. So, all of them are going to AHP. Then they have derived the landslide hazard map, and then they have validated it, right. This slide provide you the input, slope, aspect, curvature, fault density, drainage density, relative relief, geology map, lithology, distance from road, TWI, all of them are in the spatial domain, and then they have used this together in the AHP, and then they have derived this landslide hazard map. So, this green color is the low, this light green is moderate, orange is high, red is very high. So, along this highway you can see how the distribution has come, and then they have used the AOC training and testing that will help you to justify your results. In the next study, it is ensemble random forest tree with SVM, ANN, NBT and LMT for landslide susceptibility mapping in Rangit river watershed of India. So, this is the study area, This is the flow chart that they have adopted. So, here you can see this is the landslide conditioning factors. So, that is your input: slope, elevation, aspect, profile curvature, solar radiation, hillside, relative relief, drainage density, NDVI, LULC, lithology, rainfall, then distance to road, distance to river, that is being used. Then landslide inventory, and these are used together for the landslide conditioning factors selection, and this is going into the further model, right. So, finally, they have used the support vector machine, artificial neural network, naive Bayes tree and logistic model tree, and then they have derived the landslide susceptibility map, and then they have validated the result. And they, for the validation, they have used the ROC and the other statistical matrices. Here for the study, they have used the DEM from USGS, and that is the scale, and this is the output type, right. So, here you can see the complete detail from where they have collected the different parameter, or from where they have generated these parameters for the landslide studies. And this is the landslide inventory map. Here you have landslide training data set and landslide validating data set, and the altitude varies in this region between 313 to 3044 meter. Here the results corresponding to support vector machine, artificial neural network, right, and then you have the naive Bayes tree and then logistic model tree, that is given here. So, all of them are having similar result, but these are not same, right. So, how do you define or how do you justify that which one is better, right. So, for that you have to perform the accuracy assessment, and based on that you will be able to comment that a particular model is performing well for my study area. In this condition, you see the AUC is almost comparable, 0.970, 0.977, 0.976, 0.978. So, here in this case it is very difficult to say that this particular model is better, right. When we go for the landslide monitoring, continuous observation, measurement and analysis of slope movement to detect potential failure, assess risk and develop early warning system is necessary. Types of landslide monitoring: the first one is the surface monitoring, where we go for the field survey, GPS, total station and remote sensing to track surface deformation. Then comes the subsurface monitoring, installing sensor like inclinometer, piezometer, borehole extensometer to measure internal slope movement and groundwater pressure changes. Then remote sensing based monitoring, satellite based, SAR based, optical remote sensing or LIDAR data sets, these all are used, and aerial or UAV based measurement, drone with thermal, multispectral or LIDAR sensor for high resolution monitoring. Then comes the geotechnical and hydrological monitoring, uses instruments to measure soil moisture, pore water pressure and seismic activity. Real time monitoring and early warning system, automated network integrating sensors, IoT based or AI based for continuous data collection, right. So, this slide will provide you the information about how a satellite image is looking at a particular landslide, whereas the ground based interferometry or the GB INSAR that is used, then ground based LIDAR, Doppler radar, all these are used. So, here it is toppling, right. So, in this case Doppler radar will help. So, how different types of remote sensing is being used for different types of landslide studies. So, this is a concise information about the remote sensing techniques and the sensor type, platform and the key application. So here you can see the interferometric SAR. So this is basically radar interferometry. There are different sensors which are available from space, and it is good for detecting slow moving landslide, measuring millimeter scale ground deformation. When we talk about the GB-INSAR, it is real time monitoring of unstable slope, early warning for critical deformation. Then GNSS or GPS monitoring, continuous tracking of ground displacement, providing early warning system. Then light detection and ranging, this is LIDAR, high resolution surface change detection, tracking pre and post landslide deformation. Then comes the UAV based or drone based, so rapid response for landslide monitoring detection and surface cracking and movement trends. Then thermal remote sensing, so here there are few thermal remote sensing data sets available in public domain, and they are used for identifying temperature anomaly related to groundwater flow and potential slope failure. So different types of remote sensing for different types of application, right. When we combine different approaches together, how it will provide you the better opportunity to study a landslide event. So here it says the combination of GNSS, satellite INSAR and GB-INSAR remote sensing monitoring to improve the understanding of large landslide in high alpine environment. So here this is one study from this Carla et al. 2019, and the deformation field of the Bosomato landslide, Italy was generated. Geomorphological observation was combined with monitoring data from the following remote sensing system. So 3.5 years reading at 2 permanent GNSS station, 13 years reading of manually operated GNSS station, 3.5 years of INSAR data from Sentinel-1 data, 8-month measurement from a GB-INSAR. So you can see that how dedicated the researchers were to collect the data, and then they have studied the landslide. The time series of displacement measured by GNSS. So here you can see from October 2002 to April 2015, and this horizontal displacement is a millimeter. So here it is around 900 or 900 something. When we talk about the vertical displacement, so here again the same time frame, and it is in the order of 500 millimeter approximately. So here this is what they have generated, deformation by satellite SAR, and this is the cumulative deformation by GB-INSAR, right. So how beautifully they have integrated all the information to study the landslide. So this is what is needed. You have to have the dedication to study a particular landslide event. In Hong Kong landslip warning system, 40 years of progress. So here you can see it is established in 1977. This is world's first territory wide LWS. Warning were delivered for about 90% of the time there was a fatal landslide. Widespread rain gauge network, 122 rain gauges at a density of 10 km square per gauge. So here you can see how beautifully they have distributed this, and all these informations are available in their paper. This is Kong et al. 2020. And here the rainfall forecast made using short range warning of intense rainstorm in localized system. So here this is at 1 hour, right. So this is 3 to 4 p.m. This is 3 to 6 p.m. And here they have also generated the correlation between landslide frequency and rolling 24-hour rainfall data. An example of forecasted landslide occurrence alongside cumulative rainfall curves used for issuing landslip warning. So here you have the cumulative rainfall. This is the predicted number of landslide, and this is the date and time. This study is from India. It is Amrita LEWS site in Munnar, Kerala. It has been established in 2009. The key landslide types were the debris cum earth slide, complex landslide with retrogressive movement, creep landslide and debris flow. And the triggers were long duration medium to heavy rainfall, changes in LULC and anthropogenic activities in this area. A deep earth probe was used in the site to monitor the parameter in the field. The deep integrated with the IoT system for edge analytics, real time communication and powering the whole system is known as the Intelligent Wireless Probe IWP. The DEP is integrated with the sensors such as rain gauzes, moisture sensor, pore pressure transducers, strain gauzes and tilt meter, etc. So, these are some of the photographs available in their paper, and they have used the support vector machine which is a adaptive learning methodology that integrates historical and near real time data for slope condition forecasting 24 hours in advance. The algorithm is designed to function even in the absence of real time field data due to unforeseen circumstances. In such cases, it utilizes rainfall forecast data from the IMD to maintain prediction reliability. So, they are also parallelly taking the input from IMD. The forecasted slope condition are used for risk evaluation and risk control, enhancing early warning capabilities of that system. This is their website, so you can refer to that, and this app is also available in Google Play, so you can try that. So, when we talk about the early warning system, basically it has a few components which are very critical: the risk knowledge, monitoring and prediction, dissemination of information and the responses, and all of them plays a significant role in reducing the loss of life and movable property. And remember, as we discussed earlier, if failure of any part of the system will imply failure of the whole system. So, early warning system should have all these components, then only they qualify to be called as early warning system. So, with this I will end my lecture here. This module 8 is over now. We will continue the course with different hazards, and these are some of the references which have been used in this lecture. So, you can see, if you are interested, you can use these for a reference. Thank you very much.